All right, it's time to review for our final exam. So let's go through some questions. And as we do, I'll also remind you of some good things that we should be ready for and remember for the final. So here we go. So first topic here, we have our composition of functions. We want to find f of g of x. So remember, f of g of x means we're going to put g inside of f. So we're going to take f, which is 3 times x plus 4. Good way to do this is to make x a big blank spot here. And then we're going to fill that blank spot with g. So we'll put g inside of f. And we get this. And then it's just a matter of simplifying. So let's distribute this out. 3 times x over 3 is x. 3 times 4 is 12, plus the 4 that's outside. And we get x minus 8. All right, number 2, f of g of x. So f of g of x, again, we're putting f inside of g of x. Little reminder, by the way, another way to write this is f composed with g of x, and we write it this way. This is the same thing as saying f of g of x, right? So we're going to take f, which is 3 times x squared, and everywhere there's an x, I recommend that you put a blank space. So write it out like this. This is f, the outside function. Now everywhere there's an x, we're going to put g, which is 2x plus 1. All right, so we have to square a binomial now. So this is a good opportunity to review our binomial squared that you will need to memorize. And this is something that hopefully you've used a lot, and you should have it memorized. But more than just memorizing, you should know where it comes from. You can always reproduce this, hopefully, really quickly. So a plus b squared is the first thing squared, the last thing squared, plus 2 times their product. Okay? And this just comes from, you can always reproduce this a plus b times a plus b, distribute this out. We get a squared plus ab plus ab plus b squared. So it's not really a memorizing thing. It's more of, I've been there so many times that I remember. So it's a remembering thing, not a memorizing thing. This just simplifies to that. All right. So let's use that. You could write this out as uh, 2x plus 1 times 2x plus 1. But that's a lot of extra work that you're not going to have time to do on a test. So let's take those parentheses. That's going to be, we're going to square the first, which is 4x squared, square the second thing, which 1 squared is 1, and then multiply them. 1 times 2x is 2x, and double. That's 4x. Okay? So again, square the first, square the last, multiply and double. All right, let's clean that up. Distribute the 3, 12x squared plus 12x plus 3 minus 5, 12x squared plus 12x minus 2. There you go. Okay. On to number 3, f of g of x. F is 3 times x plus 5 all over 4. And we're going to put this g inside of that x. 2x squared minus 3. That's going to be, let's distribute that 3. 6x squared minus 9 plus 5 all over 4, which is 6x squared. Negative 9 plus 5 is negative 4. Now we can simplify a little bit here, but remember we got to distribute both ways, or cancel, I should say. Both ways is kind of distribution in reverse. So we can cancel 2 out from both of these. So we can divide 2 both ways here, all right? Divide this by 2, you get 2. Divide this by 2, you get 3. Divide this by 2, you get 2. We're really factoring out a 2 and then canceling. So this is 3x squared minus 2 all over 2. Okay. One more, we have f of g of x. And so we take f, 2 times x plus 4, put a blank where the x is, and we're going to put this g inside of f. So it's x minus 4 all over 2. When we multiply that 2, these 2's cancel. This is x minus 4 plus 4, and this is just x. So that tells us something. That tells us that these are inverses of each other. Now, really to check to see if they are inverses, we have to see what f or g of f of x. Now, I'm going to go above and beyond here. This was not asked in this problem. So this is bonus if you're watching this review. G of f of x says we're going to take g, which is x minus 4. So we're going to have blank minus 4 over 2. And we're going to put f inside, which is 2x plus 4. And when we simplify this, 2x plus 4 minus 4, those just make... So we can erase these parentheses first of all, right? At least in our minds. So this is just, maybe I'll write it out. 2x plus 4 minus 4. And those just make 0. So we have 2x over 2, which is x. So these are inverses of each other. Inverses undo each other. When you compose inverses of functions, you get x. So they are inverses of each other. All right. Oh, well, hey, look, that's the next question. Which of the pairs of the functions above are inverses of each other? Well, problem 4. All right. So number 4 is inverses of each other. There you go. All right, on to radical notation. This stuff comes from chapter 8. And so we're going to need to simplify these things. The key property that we're using here will be the radical product property. Okay, the radical product property says that when we have the nth root of a times the nth root of b, we get the nth root of ab. And this works both ways because it's equal. Equality goes both ways. So we can put things together and we can also take things apart. Okay? So we're going to use that a whole bunch here. Okay? So we're going to say here, we would like to take the square root, but we can't square root these. We don't know the square root of 20. We can't square root x to the fourth. Remember, when we square root a power, it divides the exponent by 2. Don't go dividing this 20 by 2. Don't get confused. Divides this exponent, all right? And 5 is not an even number, so it can't be divisible by 2. Okay? So, now, um, uh, um, some of us have this habit. Don't write this down because this is bad, all right? Some of us have this habit of writing this all out, kind of the idea, that's not the best way to go here. Okay, you're not understanding the radical product property. And if I make this y to the 51st, you're going to be writing a lot of y's out. So that's not the best way to go. So let's understand. So we want to break this up into two things, two radicals. A radical of things that we can square root and things that we can't. Now, is there a factor of 20 that we can square root? Yes, there is. It's 4. Okay, you want to keep in mind your perfect squares. Our perfect squares. You should be familiar with those up to 100 at least. 1 times 1 is 1. 2 times 2 is 4. 3 squared is 9. 4 squared is 16. 25. 36. 7 times 7 is 49. 8 times 8, 64. 9 times 9, 81. 10 times 10, 100. 11 times 11, 121. 12 times 12, 144. All right. So you should be familiar with those. Those are perfect squares. Well, which one of those is a factor of 20? 4 is a factor of 20. So we're going to rewrite this as 4 times 5. Whoops, that's not a 5. Okay. Now we can square root x to the fourth because x to the fourth is x squared squared. Okay. So a little side note here. X to the fourth is really just x squared squared. And this square root will cancel this outside squared, making that x squared. Okay, so that's what's going to happen in a second. Well, we can y to the fifth. Can we square root that? Nope. But we can square root y to the fourth. Now, I'm going to put y to the fourth there and y to the first here. This is all multiplied, by the way, all multiplication. According to our radical product property, this right here, let's see, this times this should equal this. Okay, and you should be able to go check that out. Is 4x to the fourth, y to the fourth, times 5y to the first. Is that, well, this is all multiplication. 4 times 5 is 20. I've got x to the fourth, y to the fourth times y to the first. When we're multiplying powers, we add exponents. So yes, indeed, these two things multiply to that, right? So we should be able to check that out, at least in our head, and they should multiply. Okay, they do. So we are good to go. So let's go. So we can square root. The square root of 4 is 2. The square root of, let's see, let's make that a little larger. Square root of 4 is 2. Square root of x to the fourth is x squared. Square root of y to the fourth is y squared. Now be careful here. We're not squaring this 4, we're dividing it by 2. Dividing the power by 2. Okay? And the 5y are the things we cannot square root, so we're going to leave them alone. So there it is. Okay. Onward. How about cube rooting? Well, we want to break into something we can cube root and something we can't cube root. Well, let's think about our perfect cubes. Okay, so our cubes. 1 to the third power is 1. 2 to the third power is 8. 3 to the third power is 27. 4 to the third power is 4 times 4 times 4 is 64. 5 to the third power is 125. That's good enough. That's just 5 times 5 times 5, 4 times 4 times 4, so on and so forth. So which one of these is the factor of 40? Well, looks like 8 is. 40 is 8 times 5. Again, things we can cube root, things we cannot. What about a to the fourth? Well, is that divisible by 3? No, it is not divisible by 3. But a to the third is, that power is divisible by 3. And a to the third times a to the first is a to the fourth because we add exponents. Is 9 divisible by 3? Yes, it is. So b to the ninth is what we need. And that's all of our b's. We have 13 c's. Is 13 divisible by 3? No, it is not. So, but the closest number to 13 is 12 that is divisible by 3. And c to the first. So if we cube root of 8 is 2. And cube root of 8 to the third, we're going to divide powers. Okay? We're dividing the powers. These are powers now. We're not dividing 8 by 3. The cube root of 8 is 2, because 2 to the third power is 8. So this will be 8 to the first, b to the third. 12 divided by 3 is 4, so c to the fourth, times the cube root of the leftover stuff that we cannot simplify. There we go. Okay. Now, by the way, these we should stop and think, do they need absolute values? All right. Now, there's not a reminder here, but we do need to watch out for absolute values. When do we need absolute values? Well, let's make a note right here. Uh, even indices leading to odd powers need absolute values. Okay, so the moral of the story, if we start with an even index and we end up with an odd power, we need absolute values. Okay, what does that mean? Well, here we had an even index 2, the invisible index. The index is this number that lives up here, but we don't write it when there's a 2. If that ends up being a power that's odd, we need absolute values because if these are odd, then they might end up being negative numbers. And when we square root, we always end up with a positive number. So we don't need absolute values on that example there, but let me give you one more example. Good thing you're watching this video. Square root of, let's just say, x to the 6th. Well, the square root of x to the 6th, we're going to cut that 6 in half. That's 3. So that's x cubed. Okay. Well, here we have an even index. We end up with an odd power. So we need absolute values. So this answer is not completely correct. We need to make sure that this is positive. Okay. And the whole idea is this. I don't know what x is. If I leave it like this, okay, then if x is negative 1, or let's say negative 2. If x is negative 2 to the third power is negative 8. This whole thing is negative 8. Can a square root be negative? Nope, it cannot. So negative 8 would not be an acceptable answer. So we need absolute values. That is now correct. Okay, so keep an eye out for that. If we have an odd index like 3, then it doesn't matter. Okay, if we have an odd index like 5, it's not going to matter either. Okay, so here we have two radicals. First thing we got to do is we got to put them together. So let's multiply the things under the radical. Remember, we can multiply things under the radical. If this was a plus, we couldn't do anything. We're stuck. But it's multiply. We can put them together when we're multiplying. So put them together when we're multiplying or dividing, by the way. 8 times 8 is 64. X to the 6 times x to the 4th. We add exponents. That's x to the 10th. And there's just y to the 7th. Well, now we got to simplify this. Well, how do we simplify this? X to the 5th is kind of tough. All right. I'm sorry, just a fifth index. Fifth index is kind of difficult. Well, let's think about this here. All right. This is a power of 2. All right. This is, if we take 64 and let's do a little factor tree here. 64, that's 2 times 32, which is 2 times 16, which is 2 times 8, which is 2 times 4, which is 2 times 2. So this is 2 to the 1, 2, 3, 4, 5, 6 power. So this is 2 to the 6th. So we can rewrite this as 2 to the 6th. So it's a good idea when you have a large number that you, like the 64, or a large index that you're not too familiar with, fifth powers and things like that, then it's a good idea to write it out as powers, right? Get the prime factorization of this. Now, this is where I know some of us are used to writing out a whole bunch of 2's. Okay, you can, that works, but it's kind of tedious and not always very precise. So now let's just treat the 2 the same way we would with an x or a y. So we're going to say we want to break this into things that we can take the fifth root of and things that we cannot take the fifth root of. Well, I cannot divide 6 by 5, but I can divide 5 by 5. And I'm going to put a 2 over here. So 2 to the fifth times 2 to the first. Well, 5 plus 1 is 6. Great. Is 10 divisible by 5? Yes, it is. So x to the 10th, the whole thing goes there. Is 7 divisible by 5? Nope. The closest power, smaller than 7, that's divisible by 5, is 5. And I need to put the leftover x's, x squared, over here. Because x to the fifth times x to the second. Oh, I'm sorry. Those are y's. Let's get the right letter here. Gotta learn my alphabet. That's a y. There we go. Y to the fifth times y to the second is y. Okay. Things we can take the fifth root of, things that we cannot. So let's go ahead and do that. The fifth root of 2 to the fifth is 2. And x to the 10th goes to x squared because we divide 10 by 5. And y to the fifth goes to y to the first. And then the leftovers 2y squared. Now we don't need to think about absolute value there because we have an odd index. So now we're going to go on and look at some more simplified ones. This says write the result using positive exponents. Okay, all right, so here we do need to look out for uh, absolute value as well. So we'll keep an eye out on that, all right? So we're talking about rational exponents or fractional exponents. Well, all of our power rules apply here. Here we have power to power. When we have a power to power, we multiply it. So keep these things in mind. If I have x to the a times x to the b, we add those exponents. This is going to be x to the a plus b. Okay. If I have, here, let me do this with numbers instead. That might be easier. Okay. So let's remember let's see, let's go like this. Let's say 6 and 2. Okay. So if we have x to 6 times x to the second, we add those exponents. That's x to the eighth. If we're dividing x to the 6 divided by x to the second, we subtract those exponents. That's going to be x to the fourth because 2 of these cancel with that. If I have x to the sixth to the second power, well, that's like x to the 6 times x to the sixth, which is x to the 12th. So all we're really doing is we're multiplying these. Okay? All right, there's our main ones. So remember those. Multiplying, dividing, and power to power. So here we have power to power, so let's multiply these exponents. Okay? So x, and we're going to multiply negative 2/5 times 5/4. We'll avoid that slanted fraction stuff there. All right, so this is x to the negative 10/20, which is x to the negative 1/2. Okay, and that negative power, remember when we have a negative, that drops something down to the bottom. That, sorry, becomes positive. And a 1/2 power means a square root. So this is just 1 over the square root of x. I don't know why my pen goes from skinny to thick like that. Weird programs. Okay. That's the idea. Okay. On to B here. So here we want to write these as a fractional exponent. So this is going to be a to the 6th, b to the 7th, and this 6 here is a 1/6 power. We'll raise that to the 12th. All right. Now you can do this a couple ways. Probably the easiest way right here is to go ahead and multiply these powers here. So let's do that like we did the last one. So we've got a to the 6th, b to the 7th, and 1/6 times 12 is 2. And now we can see that's pretty easy here. We end up with a to the 3rd and b to the 14th. Okay, because we have power to power, so we multiply. And this 2 applies to both of these. Now we got to watch out. Notice we started with an even index. We ended up with odd power here. So we need to put absolute values really only around that 3, that a to the 3rd. Because the even, this is going to be positive. We don't need that to be in the absolute value. If you do, it's not the end of the world. I'll accept it on the test, but that's the idea. Well, now we got a big ugly mess here. So a few things to do here. First thing we probably want to do is take care of these negative powers. If this is z to the negative 14th, it'll be positive 14 down below. And this will become positive second up top. So let's go ahead and rewrite that. 27. We've got x to the 4th, y to the 7th. Let's write a little neater. And then this z to the 2nd, that's going to go up top. Got my train coming by here. And the x to the 1st, y to the 4th. And let's bring the z down below to the 14th. And then we got this 1/3 out of here. Now let's go ahead and use our division rule, which are division or dividing powers means we subtract the exponents. So let's leave the 27 alone because it's the only number. And then we've got x to the 4th divided by x to the 1st. We subtract that. One of the x's on the bottom is going to cancel with one of the x's on top. These four y's are going to cancel with four of the y's up top, leaving y to the 3rd. Two of these z's are going to cancel with two of those, leaving z squared down there. Okay, I guess we don't need all this. And then we've got that to the 1/3 power. So now we can deal with the 1/3 power. Is that right? Oh, wait, sorry. This is z to the 12th. 14 minus 2 is 12. Okay. Now the 1/3 power means the cube root. So we're going to cube root 27. So when we cube root 27, that is 3. 3 to the 3rd power is 27. Cube rooting x to the 3rd. Now this is a power. Power to power. Multiply 3 times the 3rd is 1. So this is z to the 1st. Y to the 3rd, to the 1/3 power. Multiply 3 times the 3rd is the 1st. That's y to the 1st. Z to the 12th to the 1/3. That's 12 times the 3rd, which is 4. 12 times 1/3 is 4. And this was an odd power, so we don't need to worry about absolute value. So there's our answer. Okay. Cruising along. When we multiply powers, we add the exponents. So this is a to the 3/8 plus 2/3. Well, now we got to remember, how do we add 3/8 and 2/3? Well, we need a common denominator. So a common denominator is going to be 24. So let's multiply this by 3 on top and 3 on bottom. Multiply this by 8 on top and 8 on bottom. And we get 9/24 plus 16/24. 9 plus 16 is 25. This is 25/24. Okay. Now, notice this says, well, let's see. It doesn't say to write it in radical notation. It says write the result using positive exponents. Okay, directions don't say to write it in radical notation, so we can leave it like this. I'll go ahead and write it in radical notation because sometimes we'll want it that way. So a little reminder, this is the 24th root of a to the 25th. The denominator is the index. Okay? So this, with the instructions up above, this would be an or. But if the instructions said write in radical notation, we would need to go ahead and write this radical. Well, what about dividing here? Well, we're dividing, but we have different indices. So we can't just put those together. Well, let's see. I did just realize that we're kind of missing one type of example. So here's another bonus if you're watching this video. I'll call this F, and we'll come back to E. If we had the square root of a squared over b divided by the square root of, now let's say ab to the third. Let's take the same thing, but notice these are square roots, not 3 and 6. I just changed the problem, different problem. Well, if you have one like this, what you need to do is you need to put it together first. A squared b over ab cubed. And then you need to simplify the fraction. This would be, this a will cancel with one of those, leaving a to the first on top. This b to the first cancels with one of those, leaving b squared on bottom. And then this would be, now we can break it up into two square roots, square root at the top, square root at the bottom. Square root of a we can't do anything with, but the square root of b squared is b. Technically, it should be absolute value. So, if we have the same index, we put it together, simplify it, break it back up, and then do the square rooting. Okay, so this is a little different, but that's an important example to look through there. So glad we did that. So for this one, we have different indices. So what we need to do is we need to rewrite this using fractional exponents or rational exponents. A squared b, this is all to the 1/3 power. This is ab cubed, and that's to the 6th power. And so this is a to the 2/3, b to the 1/3, all over a to the 1/6, b to the 3/6. Oops, sorry about that. That should be a 1/6 power. Probably wondering what happened there. Now, we could simplify this, but actually I'm going to leave it alone because we now need to simplify these. But that means dealing with denominators, kind of like we did in the previous one over here. Okay, we need to get common denominators. So this is going to be a to the 2/3 plus 1/6 times b to the, oh, I'm sorry, this is dividing. Watch out. Dividing is subtracting powers. So 2/3 minus 1/6. There it is. 1/3 minus 3/6. Okay. And so we need a common denominator. Common denominator is 6. So 2/3 is the same as 4/6. And 1/3 is the same as 2/6. Okay. So we can get, this is a minus a to the 1/6 times b to the negative 1/6, which means this thing is going to go downstairs because of the negative power. So this is a to the 1/6 over b to the 1/6. And that would be an okay answer. because it doesn't say to write it as rational exponents. We could write this as, since they're both 6, the sixth root of a over b. Either one is fine. Okay. All right. So there's some good examples with some radicals. How about some radical equations? Okay. Well, to solve radical equations, we need to get that radical all by itself. Let's subtract the 3. We got square root of 4 minus x equals 2. Then we need to square both sides to get rid of that square root. 4 minus x equals 4. Okay. If we solve for x, maybe we minus 4 from both sides. Maybe we add the x to get it over on the other side. 0 equals x. There's our answer. Now, before we go any further, we need to check these. Okay, square root equations, we always need to check. So I'm going to come back over here for the check. So we've got to plug that in. So we have the square root of 4 minus, and let's plug in 0 plus 3. Is that equal to 5? Well, this is the square root of 4. Oops. Does that equal 5? This is 2 plus 3. Yes, that equals 5. We're good. Check. So that is our answer. Okay. Don't forget to check when we have square roots. Well, what happens when we have 2 square roots on both sides? Well, first thing we need to do here is we need to square both sides. But we gotta watch out. Gotta put parentheses around that when we square that. When we square the left side, we get x plus 3. When we square this side, we gotta use the a plus b squared. So we square the first thing. 1 squared is 1. Gonna leave a little space. We square the second thing. That's gonna be x plus 2. And then we're gonna multiply and double. A plus b times 2. So 1 times this is just the square root of x plus 2, and we'll double that. Now we got to get this other square root all by itself. So let's clean this up. X plus 3 equals, let's add these together. X plus 1 equals, I'm sorry, to be x plus 3. You got plus 1 and plus 2. And let's get the x's out of there. Well, it looks like these just go away. Isn't that convenient? So this one works out really nice. Doesn't always happen this way. 2 square root of x plus 2. Got to divide by 2, divide by 2. So 0 equals the square root of x plus 2. And we got to square it to get rid of that square root. And so 0 equals x plus 2. So x equals negative 2. So we got one answer. And so we got to check that one answer out. So let's go to check. So is the square root of x plus negative 2 equal to 1 plus the square root of negative 2 plus 2? Well, this is going to be square root of, what did I just do there? Sorry, I was writing and not thinking. We're going to plug negative 2 in here. Negative 2 plus 3. Negative 2 plus 3. So it's the square root of 1 equals 1 plus the square root of 0. Is 1 equal to 1? Yes, it is. So our answer works. One more radical equation here. Let's square both sides. We get x squared. Okay, now we're going to do our binomial squared. Square the first, square the last, multiply, and double. 1 times x is at 1x, doubled is 2x. Okay, if you need to write it out, write it out. But it's better if you don't have to. then we're going to, all right, we got a quadratic here. So we need to subtract 2x from both sides. We need to make it equal to 0, right? Okay, quadratics is chapter 9. So we end up with the 2x's go away. It's a minus 2. And actually, because the x's went away, we don't need quadratic formula or anything like that, or factoring. Let's go ahead and add 2 to both sides. X squared equals 2 and square roots. Now this one comes out kind of weird because it's a square root. So we do get plus or minus. Don't forget that. Okay. So plus or minus square root of 2. All right. Square root of 2 is about 1.414 if you plug in your calculator. Okay. Plus or minus 1.414. So probably the easiest way to test this out is if you go to your calculator and let's check x equals positive the square root of 2, and that's going to give us so we plug in the square root of 2 plus 1. Go plug that into your calculator. You're going to get 2.414 about. And if you plug in the square root of 2 times the square root of 2 plus 3, all right, if you type that thing in your calculator, you should also get 2.414. That checks out. If you plug in the negative version, well, you get negative, x equals negative square root of 2. So we get negative square root of 2 plus 1 equals, well, we can actually stop right here, okay? You'll see why in just a second. Okay. So this is negative 1.414 plus 1, which is negative 0.414. And I don't even need to type all this because what's wrong with this picture? Can you have a square root that's equal to negative? No, you cannot. That doesn't work. Okay, so we have an extraneous answer. The only correct answer is x equals the positive square root of 2. Okay, the negative one, it doesn't work. Okay, so a little weird with the square root there. I wouldn't give you one like that on the test, but it's good to see that it still works. Okay, we just check it out. That's the big idea. You get an answer, and you check them out to see if the left and right come out the same. All right, moving on to some quadratics and quadratic functions. We have two types of quadratic functions you need to be familiar with. We have quadratic functions in standard form. And standard form is y equals ax squared plus bx plus c. We also have quadratic functions in vertex form. And vertex form is y equals a times x minus h squared plus k. And these are useful for different things. Okay. Vertex form is useful because it gives us the vertex is at h comma k. And since the vertex is at h comma k, the axis of symmetry, which goes right through the vertex, is at x equals h. Okay. If we have standard form, well, we have an equation for the axis of symmetry. And the axis of symmetry is at x equals negative b over 2a. And that's something we want to memorize. Now, a little side note for memorizing that. Remember your quadratic formula that we use to solve quadratic equations? X equals negative b plus or minus square root b squared minus 4ac all over 2a. And that will be given to you on the final exam. Okay, so that'll be given to you. And hidden in the quadratic formula is the axis of symmetry. You see it right here? negative b over 2a. There it is right there. That's the axis of symmetry right here. Okay? So the quadratic formula, it starts with the axis of symmetry, negative b over 2a. Okay, so that's the axis of symmetry. To find the vertex for this vertex, we've got to plug in x equals negative b over 2a. So you just plug that in and you get the y value. So the vertex is at an x value of negative b over 2a and a y value of, we'll say, f of negative b over 2a. In other words, you got to plug it in. Okay? If y equals f of x. Okay? All right. So those are kind of some important things there. We're also going to talk about x-intercepts. To find x-intercepts, all the x-intercepts happen when y equals 0. The y-intercept happens when x equals 0. Okay? And so doesn't matter which form you have, plug in 0 for x and you get the y-intercept. Plug in 0 for y and you can find the x-intercept. Okay? All right, so those are key things to remember. Okay, let's work on that here. So we have an axis symmetry, which we just reviewed. X equals negative b over 2a. Negative b is negative 4 over 2a. A is 1. So that is 4 over 2, which is 2. The axis of symmetry is an equation. X equals 2. Do not say that the axis of symmetry is just 2. It's an equation. X equals 2. So to find the vertex, we need to find f of 2. So that's going to be 2 squared minus 4 times 2 plus 3, which 2 squared is 4. 4 minus 8 is negative 4, plus 3 is negative 1. 4 minus 8, negative 4, plus 3 is 1, negative 1. Yep, sounds good. All right, so the vertex is at 2 comma negative 1. Okay, so we're going to be graphing this. Let's go ahead and before we go any further, let's go ahead and graph this. We need to label our graph. 1, 2, 3, 4. You put at least one number on each axis. We're going to go by ones. That'll be okay. And then we've got an axis symmetry at 2. You don't necessarily need to draw this line, but we will. And 2, negative 1. There's our vertex right there. Okay. We need x-intercept, so we're going to plug in 0 for y. F of x is the same as y. So 0 equals x squared minus 4x plus 3. And we could try to factor this, which this, I think, does factor. This factors into x minus 3 times x minus 1. Those numbers add to, these add to negative 4 and multiply to 3. And so we set these equal to 0. X minus 3 equals 0. X minus 1 equals 0. And so our x-intercepts happen at x equals 3 and x equals 1. As points, this is 3 comma 0 and 1 comma 0. So 1 comma 0 and 3 comma 0, we can locate those there. The y-intercept, okay. The y-intercept, let's plug in 0 for x, which just means let's find f of 0. And that would be 0 squared minus 4 times 0 plus 3, which is 3. So this would be the point 0 comma 3. So 0, 3. That fits our parabola. 1, 2, 3. Here it is. And for graphing purposes, we know that parabola is symmetrical. So that's 2 away from the axis symmetry. If we go 2 away over here, we have this point right there. Okay. We can also, once we know the vertex, and once we know the a value here, the a value is 1. That means it's going to look like our standard parabola. Our standard parabola, y equals x squared. When you're graphing x squared, hopefully you're very familiar with that. We get 0 squared is 0, 1 squared is 1, 2 squared is 4, negative 1 squared is 1, negative 2 squared is 4. So with that, from the vertex, 1, 1, from the vertex, we can go right 1, up 1, there's a point. 2, 4 means from the vertex, go right 2, up 4, there's a point. Negative 1, 1 means from the vertex, left 1, up 1. Negative 2, 4 means from the vertex, go left 2, up 4. We know it's going to have the same shape as y equals x squared. And there's our parabola. So we could also got our points there, but we had to find them using we had to find these things anyways over here. Well, what's the domain? The domain is all the possible x values. Okay. The possible x values go from negative infinity to infinity. The range is all the possible y values. So these are x's. These are y's. The possible y values, we'll notice it doesn't go below negative 1 over here. So the lowest y value we get is negative 1. Oh, but that is included, so we need a hard bracket, a square bracket there. And it goes up forever and ever. So there's our range. Okay. All right. You might pause this and try this if you haven't already. But same process. Axis symmetry. X equals negative b over 2a. A is 1. So it's negative 3 halves. Okay. So our axis symmetry as x equals negative 3 halves. That's negative 1.5. 1, 2, 3, 4, 5. Let's put 5 here. 1. Okay. So 1.5. There's our axis symmetry right there. Again, you don't have to draw that, but I'll put it for us. To find the vertex, we need to plug in that. We need to find what g of negative 3 halves is. Going to be a little tricky with the fraction, but we can do that. Negative 3 halves squared plus 3 times negative 3 halves minus 4. All right. Squaring gives us 9 fourths plus, actually minus, because 3 times negative 3 is minus 9 halves minus 4. And let's change that 9 halves to quarters. That would be 18 quarters, 18 fourths. And while we're at it, let's change 4 into 16 fourths. Let's see. So 9 minus 18 is negative 9. Negative 9 minus 16 is negative 25. Oh boy. Negative 25 fourths. Not the prettiest, but there you have it. Good fraction practice, huh? So our vertex is at negative 3 halves and negative 25 fourths. Okay, again, good practice with fractions. I don't know that you would get one this complicated on the test, but if you can do this, you can do anything, right? Negative 25 fourths that's like negative 6 and a fourth. So 1, 2, 3, 4, 5, 6 and a fourth. Right about down here. We can find our x-intercept by plugging in 0 for y. So 0 equals x squared plus 3x plus 4 minus 4. Does that factor? Let's see. How about two things that add to 3 and multiply to negative 4? That would be x minus plus 4, actually, times x minus 1. And so that gives us x equals negative 4. What makes the first one 0? What makes the second one 0? And so our x-intercepts are negative 4, 0, and 1, 0. Okay. So negative 4, 0, and 1, 0. Okay, 1, 2, 3, 4. There it is. Last but not least is our y-intercept. It means we've got to plug in 0 for x. Plug in 0 for x. That gives us g of 0. And that's going to be 0 squared plus 3 times 0 minus 4, which is negative 4. So that's going to be 0, negative 4. Okay. 0, negative 4 looks like right here. And we have a mirror image over here. So there's our parabola. A little funky because of the fractions. But that's the idea. Okay. All right. And domain is all real numbers. That's always true for quadratic functions. The range, well, the lowest x value is negative 25 fourths, or negative 6 and a fourth would be fine. And we go up and up and up to infinity. Those are the y values. Okay? All right. So that's the process. Same process whether you're dealing with whole numbers or fractions. All right. Lots of stuff here. Hopefully this is helping some. We'll keep trying to go quickly here. You can obviously skip around. That's the beauty of videos, right? So here we're going to solve some quadratic functions algebraically. We have some different methods. So we're going to go ahead and this one we want to get the squared all by itself. Don't multiply this out. It's very tempting to multiply it out first. Now we're going to use the square root method because if we can get that squared by itself, we can square root both sides. Okay. Now we know about complex numbers now. So imaginary numbers. So we're going to get a plus or minus answer. And since this is a square root of a negative number, then this is going to be 2i. And now we need to subtract 3 from both sides. And x equals plus or minus 2i minus 3. But we like to put the non-imaginary number first, the real part. And there it is. Okay. All right. For this one here, where the square root method's not going to work because it has a 5x in there. So let's get everything to one side. Let's set it equal to 0. We want to get that out of there. We want to get the 4 out of here. Now, be careful. I know I wrote that minus 4 under there, but 5x minus 4 we can't combine. That's plus 5x minus 4. Now we can try to factor this. Two numbers that add to 5 and multiply to negative 4. And you can keep looking, but I don't think they exist. So let's go ahead and use our quadratic formula. You can either use completing the square or quadratic formula. So probably want to complete or use a quadratic formula would be best here. Quadratic formula, it will be given to you on the test, but you should have it memorized. X equals negative b plus or minus square root b squared minus 4ac all over 2a. Okay, so let's use that here. We've got x equals negative b, which is 5, plus or minus square root b squared minus 4 times a, which is 1. There's a 1 right there, times c, all over 2a. Now, almost 99 times out of 100, I'll say, if you're going to make a mistake, it's going to be right here. Okay, so let's do this. This is called discriminant. The discriminant needs to be evaluated carefully. Okay, so just do your order of operations and you'll be fine. So we have, we have x equals negative 5. So let's take care of that discriminant. Now, The best way I think to think about um, this is -4 or plus -4. So if you think of this as plus -4, then we have -4 times 1 times -4. Well, that negative times a negative is a positive. So we have 25, that's 5 squared, plus, because I changed it to a plus, I made it plus minus there, and this would be a positive 16. Okay? Be very careful there. If you're going to make a mistake, it's right here with this negative, most likely. You can make it other places, but watch out for that. Okay? -5 plus or minus, this is the square root of 41 all over 2. Now, I don't know what the square root of 41 is, and it can't be simplified. Is there a perfect square that goes into 41? I don't think so. So we leave it alone, and that's good enough right there. Okay? Moving on. All right. This got a bunch of stuff going on. We're going to need to just clean it up and set it equal to 0. So distribute that 3 and let's move everything over. Let's subtract x from both sides and add 4. That gives us 3x squared minus 4x plus 4 equals 0. And again, we are going to need the quadratic formula. So x equals negative b. Watch out, that's -4 plus or minus square root b squared minus 4ac all over 2a. Now notice I'm putting these in parentheses. Okay, that's because you can easily make mistakes here. Here's another place. It's negative from the formula and the negative from the problem or the expression. Here we have -4 squared. That's going to become positive. If you don't put these parentheses there, you're going to write -16. It is not -16. So let's clean it up carefully. This is all just doing order of operations. We have -4 squared, that is positive 16. And we have, now notice this is like a -4 times a 3 times a positive 4. Well, there's only one negative here, right there. So it's minus 4 times 4 is 16. 16 times 3 is 48. All over 6. And 16 minus 48, that should be 32. Okay, negative 32. Getting close. All right. Well, let's go on up here. We have 4. -32. First of all, it's negative, so it's going to have an I. And then 32 breaks up into 16 and 2. We need to simplify the square root of 32. And that's all over 6. So cleaning it up, x equals 4 plus or minus. Square root of 16, we know that's 4. There's the I. All over 6. Now, when this is a imaginary number or a complex number, we want it in the form a plus bi, which means we want to go ahead and divide out this 6. Divide both of these by 6. Let's write it as two fractions. We have 4 sixths plus 4 squared root of 2 over 6. And we're going to pull that I out in front. Right? So we can clean that up a little bit. This is 2/3. This is 2 squared root of 2 over 3. So you can cancel out the 2 here, 2 from top and bottom, but the square root of 2 is going to stay there. I. There should be a minus there, plus or minus. Okay, that's our answer. So complex numbers get written out as a plus bi. All right, all right. Well, this one we need to multiply out first and clean up. So distribute that this binomial out. X times x is x squared minus x plus 2x minus 2 equals 6. So x squared will minus 6 from both sides here. And this is going to be a plus x and minus 8. And we can't factor. We could use completing the square, but since completing the square, by the way, works good when this is 1 and this is even. If this is not even, we're going to end up with fractions, which get a little messy. But if this was even, and this is 1, I would say use completing the square. It works pretty nice. But let's go ahead and do our quadratic formula. X equals negative b plus or minus square root b squared minus 4 times a times c all over 2a. If you don't write this out, you're just playing with fire. Okay? You're gambling. You're going to lose points on your test probably because you'll get things wrong. Okay? So write out your quadratic formula, then do your careful order of operations. This is like a negative 4 times a negative 8 is positive. 4 times 8 is 32 times 1 all over 2. And this just gives us negative 1 plus or minus the square root of 33. And we can't do anything with the square root of 33, so we just leave it. Okay. But the key to that one is multiply it first, set equal to 0, then use a quadratic formula. Well, on to chapter 10, which is using exponents and logarithms, exponentials and logarithmic functions. The key here is our definition of a logarithm, our key property, or key definition really is what this is. Okay, and so that gives us that we know this. If we have y equals b to the x, well, we can rewrite this. We can, b is the base, so we can swing that base around, and we can rewrite this as log base b of y equals x. Okay, and the key here is that these two things are equivalent. So if you have something that's in an exponential form, you can rewrite it as a logarithm. If you have something that's in a logarithmic form, you can rewrite it as exponential. Okay? So that's the key relationship or the key property there. Okay? And that's really the main thing you need. The only other thing you need is a change of base that we're going to use. So our change of base formula, you'll need to memorize this. And that is this. If we have a log base b of m, that's the same thing as natural log of m over natural log of b. Or if we want, we could say log base b of m is common log, which is base 10, over common log of b. So notice there's no base. That means it's base 10. All right? So it doesn't matter which one you use, you're going to get the same answer. But we use this to help us get a decimal. So let's use those things. So using our key property here, we want to get the exponential by itself. So we want it to look like something to the x power so we can change it into a logarithm. So we're going to subtract 2 from both sides. And that's going to give us 8. Let's divide by 4, trying to get that exponential all by itself. And we got 5x plus 3 equals 2. Now we're going to change this to a logarithm. Now, if you've been cruising YouTubes, you have another method. I'm not going to go over that right now. Using properties, we didn't go study other properties. You don't need them. All you need is this. You need this property right here, this definition. If it's an exponential, we're going to change it to a logarithm. Here's how we're going to do that. We're going to take the base 5, and we put it underneath that 2, and this will be log base 5 of 2 equals the power, which was x plus 3. There it is. Now log base 5 of 2 is just a decimal number. We'll find that in a minute. But let's go ahead and solve that. Subtract 3. And we end up with the exact answer. The exact answer is that pin thing again. X equals log base 5 of 2 minus 3. This is the exact answer. Okay, that's an exact answer. Log base 5 of 2 is a decimal number. So let's go ahead and find that with our calculator. In order to find this, we need to do a change of base. So change of base means natural log of 2 divided by the natural log of 5. And then while we're at it, we can subtract 3. And if you go plug that into your calculator, you're going to get a decimal. And that comes out to be about negative 2.57. Okay. All right. Well, let's solve this up. We want to get that exponential all by itself. Let's divide by 10. E to the 4t equals 12 tenths. We could just leave it like that for now, it's fine. Can make it 6/5, I guess. And now we need to change it to exponential. So we swing the base around. The base is e. E is our natural number, about 2.71828. So log base e of 12 tenths is 4t. Now, we have another way of writing log base e, right? We usually don't write it like I just did. That is our natural log. So that's what ln means. Maybe while I'm at it, I'll go ahead and write that as 6/5 equals 4t. Okay? And we're trying to keep things exact for right now, so we'll leave it as ln of 6/5. Let's divide by 4. And there's our exact answer. T equals the natural log of 6/5 divided by 4. That's exact. If you go punch on your calculator, you'll get about 0.05. Okay. Okay, so those are exponential equations. We had to change them into a logarithm to solve it, and use a change of base on one of them there. If it's a logarithm, so if it's a logarithmic equation, we're going to change it into exponential to solve it. Okay, so if it's exponential, change it to logarithm. If it's a logarithm, change it to exponential. So let's take this base, swing it around. So this is 3 to the third equals 4x plus 5. You see how easy that is? Okay, we don't need extra properties or anything. 4x plus 5 equals 27. Subtract 5. 4x equals 22. Divide by 4. And there's our answer. 22 fourths or 11 halves or 5.5 if you want. That's it. Okay. And D here, if we subtract 4, 2 log x minus 5 equals 8. Divide by 2. And so log of x minus 5 equals 4. Now, what's our base here? There's no base written. Remember, if it's not written, and now if it's ln, the base is e. If it's a common log, the base is 10. Common log means, well, it's common, like we have 10 digits, we have a base 10 number system. So this is 10 to the fourth. And 10 to the fourth is just a 1 with 4 zeros after it, also known as 10,000. And so if we add 5, we get our answer. 10,005. All right. So if it's a logarithm, we change it to an exponential and solve it. If it's an exponential, we change it to a logarithm and solve it. Domain, we've learned about a few different functions. Domain is the possible x values. If we have a square root of x, the thing underneath the square root must be greater than or equal to 0. And we write that in interval notation as 0 to infinity. There's our domain. Okay. Here, the thing under the square root, 3x plus 10 must be greater than or equal to 0. So we write the inequality. We solve it like we would an equation. Negative 10, divide by 3. And so we see x is greater than or equal to negative 10 thirds. In interval notation, that means it includes negative 10 thirds. And it goes up to infinity because it's greater than. Okay. One little note on that, one more little example. If we have f of x equals the square root of, let's say, 8 minus 2x. Well, 8 minus 2x must be greater than or equal to 0. If we subtract 8 from both sides, negative 2x is greater than or equal to negative 8. And we divide by negative 2. Now watch out. Whenever you multiply or divide by a negative number with an inequality, you've got to flip the sign. So we divide by negative 2, so we flip it. So this example here would be from anything less than or equal to 4. So before going down to negative infinity, right? So sometimes you got to flip the inequality if you divide by a negative number. Okay, a quadratic. Well, all quadratics have all real numbers. So all real numbers from negative infinity to infinity. Exponential equations. You can put anything in an exponential equation. You can say e to the positive numbers, e to the negative number, e to the 0. So that's all real numbers. But inside a logarithm, you can only put numbers that are positive. You can't put 0, but anything bigger than 0 you can put. So 0 is not included. And we go up to infinity. Make sure you have a soft bracket or a round bracket here. Notice up here we had a square bracket because you can put 0 in a square root, but you cannot put 0 inside a logarithm. Okay? If you say log base, whatever, 10 of 0, what is the power you put on 10 to get 0? It's impossible. There is no number you can put on 10 to get 0, so that's why we can't do that. So again, any logarithm, 4x plus 2, the stuff inside must be greater than 0. So subtract 2, divide by 4, x is greater than negative 1/2. So negative 1/2 to infinity, soft bracket, round bracket, okay? All right. Now, we're going to find some application problem answers here. We want to find them algebraically. Now, if you have a graphing calculator and you're allowed a graphing calculator on a test, you can graph this. And you can go find intercepts and things like that and vertices. And that's good. You should know how to do that. But we also need to find it algebraically. If you want full credit for this problem, you need to find it algebraically. Okay? So, here we have a situation. Sweet Harmony Crafts has determined that when X hundreds of Dobros are built, the average cost is C. So the more Dobros you build, the cost goes down, okay, because of mass production kind of things. So if we have 600 Dobros, that means X equals 6. What is the cost? Well, we're just going to find C of 6. And so we should write this out. 0.1 times 6 squared minus 0.7 times 6 plus 2.425. And it's a 6, not a 0. If you plug that in your calculator, you'll get $182.50. Well, now the question is, what's the cost at $300? Okay, so notice that this says X hundreds are built, the average will cost, and this is in hundreds of dollars. Okay, so we want C of X to be 3. And so 3 is going to be equal to 0.1x squared minus 0.7x plus 2.425. Kind of ugly because of all the decimals, but this is where we can, we want to solve this with the quadratic formula. So 0 equals 0.1x squared minus 0.7x minus, and if we subtract this, we'll get 5, a negative point, what, 575? That should be right. Now, if we go to our calculator, we can use our quadratic formula. X equals negative b equals 0.7 plus or minus the square root. And I'd strongly recommend you write this out right before you type. Many people are tempted just to go start typing things. Don't go start typing things until you write it out. Negative b, so that'll make this positive 0.7 minus 4 times a, which is 0.1, and C is negative 0.575, all over 2A, which is 2 times 0.1. Okay. Now, a lot of people have been having trouble with this. Here's what I would recommend. I'd recommend typing out the discriminant just like it is. Don't do this in pieces. I see some people try to do, they multiply this, then they multiply the 4, then they da 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 da. No, do this whole expression in the calculator. So check it out. Here's what I would recommend you do with your TI-84 calculators. Okay. Uh, get that discriminant. Now, this discriminant won't always come out to be such a simple number. Usually it'll be even longer than this. Well, sometimes that's not necessarily true. Okay. It should come out to be fairly terminal or terminating decimal. So we carefully type those in. Make sure you use the negative, not the minus here. This is a minus, this is a negative. If you do a negative button instead of the minus button, you'll have problems. Okay, this is a negative, this is a minus. Okay, so calculate that, get that, and then the whole, now, first of all, this minus negative, just make that a positive. Do that in your head. That should be easy enough. So this whole numerator needs to be in parentheses. But instead of typing that business, I'm going to type 0.93. And so I have, in fact, let's go ahead and write this out. So I should rewrite maybe even before I type. So x equals 0.7 plus or minus the square root of 0.93 all over, and you could do this 2 times 0.01 if you want. That might be a good idea, because it's simple. Do the simple stuff in your head, okay, or on paper. And then go to your calculator, put parentheses around the whole top, divided by the parentheses of the whole bottom. Okay, or if you just do it in your head, you don't need the parentheses there. Okay, then we need to do the plus version because it's plus or minus. That comes out to be 8.32, or the minus version, minus. Okay, so there you have it. Watch out. A lot of mistakes on that people make. We want the positive one. So x is 8.32, and this is in hundreds, right? Okay, so when will the cost? So we want 832 dobros. 832 dobros. Okay, and we should probably write it out as a sentence. 832 dobros will make the cost $300, like that. Okay, so 832 dobros. Let's fix this. A dobro, by the way, is a musical instrument. If you didn't know, dobros. Okay, makes the cost. We say $300. All right. Okay, moving right along. What's the minimum average cost? Well, minimum, whenever you're talking minimum, we want to find the vertex. So we need to find the vertex. Where does the vertex happen? So minimums and maximums happen at the vertex. The vertex happens when x equals negative b over 2a. Okay, so that happens at negative b, which is negative 0.7 all over 2 times 0.1, which is just 0.7 divided by 0.2. And that's just same as 7 divided by 2, which is 3.5. So x happens at 3.5. So we need to find c of 3.5. C of 3.5. So if we go plug that in, 0.1 times 3.5 minus 0.7 times 3.5 minus 0.575. That is going to give us 1.2, which means the cost is $120. Okay. So what is the minimum average cost? Okay. So the minimum average cost is $120 at 350 dobros. Okay, so 3.5 means 350 instruments. Okay, all right, there we go. Minimums, maximums happen at the vertex, and we can solve for x, we can solve for y, like we just did. Last little example here is an exponential example. So, population of Austria is about 8.2 million in 2009, an exponential growth rate of 0.052%. Write the exponential function describing the population of Austria 2 years after 2009. Now, on the final, you'll be given a formula sheet that looks like this here. And so you'll have some formulas. For interest rates, we have these exponential formulas here. This is continuous compound interest. This is compound interest, and this is simple interest. This is our general exponential growth function. That's what we're going to use here. And so we have our initial value, P0, and our initial population or quantity, our new quantity, and K is the growth rate. T is time. Okay, so there's that. All right, so we're going to use that formula right here. P of t equals P0 e to the kt. Okay, So again, you don't have to have that memorized. That'll be given to you. Okay. So this just says, go ahead and write an exponential function describing the population of Austria t years after 2009. So we've got to just write the function. Our initial population is 8.2. So the new population is the original population times e to the 0.052. Now, I just noticed there's actually a typo in this problem, all right? So this should be 5.2%. So this got kind of mixed up. We can either say the growth rate is 0.052 or 5.2%. 5.2% is equal to 0.052 because we moved the decimal two places. Okay, so I'll need to fix that problem on this handout there. All right. So let's go with the 0.052 as our k value there. So that's it. That's our function. So the question is, what will the population be in 2020? Well, this is years after 2009. So let's subtract 2009 from that. And so that would be when t equals 11, we get p of 11, which is 8.2 e to the 0.052 times 11. Okay, now again, you got to be careful how you type this. I'll show you that here. We'll pull the calculator up. And then 2050, that would be 2050 minus 9 would be 41. So that would be P of 41. So we have 8.2 e to the 0.052 times 41. So when you go type this in your calculator, just type the whole thing in there. Depending on your calculator, you might use, when you type E, you might get the caret key here. You should put this whole thing in parentheses because we need that needs to all be in the exponent. Okay. And so anyways, we get, looks like 14.2. Let's move this guy out of here. 14.52, I guess. So this would be 14.52. We've probably round that to 3. And this is 69.14. And the units there, the units are, these are million, right? Okay. And that's okay to write that way. When will it be 9 million? Well, we're going to write 9 equals 8.2 e to the 0.052 t. And let's solve this up. We're going to divide by 8.2. Divide by 8.2. Now, I would just, you could do that and you'll get a decimal, but it's probably best just to leave this. So we have 9 divided by 8.2 equals e to the 0.052t. And let's go ahead and change this to a logarithm. Swing that e around. And we're going to have, let's go up here. Log base e, which is the natural log of 9 over 8.2 equals the exponent 0.052t. And then let's divide both sides by 0.052. Okay. And if we do that, we get 1.79. Okay. So add 1.79 to 2009. And we can say that that's 2010.79. Okay, so we can say during 2010, the population will reach 9 million. Okay, 9 million. Okay, All right, last but not least, what's the doubling time? Well, that just means we're going to take that 8.2 and double that to 16.4 equals 8.2 e to the 0.052 t. Solve that the same way. Divide by 8.2, divide by 8.2. There's our 2 for doubling. You can jump right to that. We just want this e factor to be doubled. And so we can do the natural log of 2 equals 0.052t. Again, we're just swinging that base around using our definition. Change it into a logarithm. It's an exponential equation, so we change it to a logarithm equation. Divide by 0.052. Go plug that into your calculator, and you should get 13.33 years. Okay, and that is the doubling time. Okay, well, hopefully that helps. A lot of stuff there. And on the last page of the review there is the formula sheet, so you might note that because you will be able to use that. And so keep studying hard. Understand those big ideas of exponential equations and logarithmics equations, quadratics, and radicals. So those are our 4 functions that we've studied in this course. So, all right, thanks a lot. And just to wrap it up, these are the formulas you'll have on our tests there. So you don't have to memorize these. You'll be provided with these to help remind you how to do some of these little things. So keep your eye on the big ideas and get those down well, and all the other little things will come.